This lesson is part 2 concerning the classification of groups. I'm also going to talk a little bit about subgraphs and isomorphic graphs towards the end of this lesson. The next type of graph I want to talk about is a bipartite graph. And I have a couple examples down here. Basically, you have two sets, U and V, and all the elements of U have an edge to all the elements of V and vice versa. So you can see here the black elements in this graph here could be our set U, and then the red one's the set V, and you notice that you have connectivity between all the black and all the red, but key point here is you don't have any edges between the elements in set U or any edges between the elements in set V. So this is called K32. The 3 and the 2 refer to the number of elements in U and the elements in V. And then this is K33. You just have 3 elements in U and 3 elements in V. All right, and these are known as complete bipartite graphs. And you can have you could have 5 and 7 or any two numbers here, any two positive integers here for the number of elements in U and V. So these are just two examples. And another note is you could have an incomplete bipartite graph. So for example, if we took this one here and let me just draw on it, and let's say we deleted that edge, this would still be a bipartite graph, but it would be incomplete because we don't have an edge between these two vertices. On this slide I have a theorem about bipartite graphs, and they don't need to be complete. They can just be any bipartite graph. In other words, it has this condition here. The vertex set can be partitioned into two parts, U and V, so that no edge joins vertices in the same part. And the added condition for being complete is not necessary for this theorem here. It holds for this general condition. Okay, so the theorem goes as follows. The graph G is bipartite if and only if it contains no odd cycles. We have to prove this in two directions since it's an if and only if theorem. Assume G is bipartite with vertex sets U and V. Every step edge along the graph goes from a vertex in U to a vertex in V, or from V to U, to state it the same way. So to return to a given vertex, it takes an even number of steps. Therefore, there can be no odd cycles in this if G is bipartite. And going in the other direction, assume that every cycle in G is even. And we'll prove this more generally. G could be composed of multiple disjoint graphs. So we'll just take any one of those. We'll call it, let's take G1 as one of the components. And then if we prove the theorem for that component, of course, it'll hold for all the other components. So let x sub 0 be a vertex in G sub 1. For every other vertex x in G sub 1, let d of x be the length of the shortest path from x0 to x. And we'll use this definition here to divide our component into the sets U and V. So for every vertex in G sub 1 whose distance from x sub 0, or should I say its shortest distance from x sub 0 is even number of edges, color the vertex white. And we note that x sub 0, x is 0 distance from itself, since 0 is an even number, and thus that would be colored white. And then we color the other vertices of G sub 1 black, i.e. vertices whose distance from x sub 0 is odd. So the white and black vertices, as defined above, constitute the two parts of a bipartite graph G sub 1, since if G sub 1 had an edge between two white vertices or between two black vertices, it would have an odd cycle. To see this, consider the case of two adjacent white vertices A and B. A similar argument holds if we had an edge between the two adjacent black vertices. So we have two possibilities, and I'll talk about those on the next slide. So we have the two cases I mentioned on the previous slide, and I've drawn them here. If the white vertices A and B are on the same path, P from x sub 0, so in other words, this path here, the distance between A and B along P is even. In other words, the distance from A to x sub 0 is even, and the distance from B from x to x sub 0 is also even. Then the distance between A and B is also even. The edge directly between A and B and the part of P between A and B, this here, constitutes an odd cycle, which contradicts our assumption. So this is the figure here. That would be the red. And of course, it doesn't need to be 2 here. I draw it as 2, but it could be any even number that has the distance between A and B. And when you have this edge, if you assume you have an edge directly between A and B, then that gives you an odd cycle. Then the other case is where you have A and B on different paths from x sub 0. So this is even. This part, what I'm pointing to here, this has an even number of edges, right? That's by the definition of how we define the white vertices. And then this would be even again from x sub 0 to B. And then if we assume there was an edge directly between A and B, then we would have an odd cycle. So again, we contradict our initial assumption that all the cycles were even in our graph, or our subgraph G sub 1. Thus, G sub 1 is bipartite. We can do the same for each component of G. So G is composed of one or more bipartite graphs, and thus is bipartite. I didn't actually define that, but that would be the definition more generally of a bipartite graph, that each component, if you have a graph with disjoint components, each component would need to be bipartite in order to classify G as bipartite. Okay, so this was a little bit involved in terms of the proof going the opposite direction. I have a more concise proof on the next slide. You can decide which one you like better out of the two. On this slide, I have the alternate proof of the second half of the theorem that I mentioned previously. So here we want to show that if there are no odd cycles in a graph, then the graph is bipartite. So it starts off pretty much the way my initial proof went, and it varies a little bit, and we'll see how that goes. So assume G contains no odd cycles. So this is our graph. Choose a vertex V and a connected component G sub 1 of G. So we're allowing for the case where G has multiple components, and then we'll show each one of those components is bipartite under this condition here. We let U be the vertices whose shortest path from our vertex V is even. So this is like our x sub 0. I guess I could have used the same variable, but I changed it to V here. And then let capital V equal the vertices whose shortest path distance from V is odd. Clearly, every vertex belongs to one set or the other, but not both. So we've divided our set G, or graph G1 into two sets of vertices. And for it to be bipartite, we need to show that there aren't any edges between the vertices in U, and there aren't any edges between the vertices in V. And we can just show it for either U or V because it's symmetric, and we'll do that in a second. So now suppose there was an edge joining two vertices in U. We want to get a contradiction here. Let those vertices be x and y. Then, by the way, we've defined U. The distance from v to x is even, and the distance from v to y is even. Traversing the path from v to x, then the edge xy, this edge here that we assumed, and then returning to v along the path y, v, produces a closed walk. It's a key difference here from the previous proof. It's a closed walk in the sense that the edges may overlap, which potentially could cause a problem. So this is not necessarily a cycle, but there's a way of solving that. So anyway, this closed walk has length, the distance from v to x plus 1, in other words, this one edge, then the distance from v to y. And since this distance from v to x and this distance from v to y are even, and we added a 1 to it, we get an odd number. Thus, G sub 1 contains a closed walk of odd length. However, there's a lemma that states that every odd closed walk must contain an odd cycle. So that's what gives us our contradiction, that we had an edge between two vertices in U. As I mentioned, the argument is similar for V. Thus, every edge joins a vertex in U to one in V, and there aren't any edges between the vertices in U, and there aren't any vertices between the edges in V. So G sub 1 is bipartite. Repeating this argument for each connected component within G shows that G overall is bipartite. Okay, so that's the alternate way. It seems a little bit cleaner, but then you have this lemma here, which makes things a bit more complex because we need to prove that, which I'll do in the next slide. So let's prove the lemma I mentioned. Every closed walk of odd length contains an odd cycle. So just to remind you, closed walk means you can return to the vertex from where you started, but you may overlap or repeat some of the edges. And an odd cycle doesn't have any repeats. You only hit each edge once on your path back to your starting point. So let v sub 0, v sub 1 up to v sub k be a closed walk where the first vertex and the last are the same. So in other words, you come back to where you started, and let k be odd. And we want to show that there's a cycle inside of this closed walk. If the walk has no repeated vertices other than the first and last, it is already a cycle, and since k is odd, it is an odd cycle. So in that case, we're done. So we assume that there is a repeated vertex. So we'll suppose that that's U, and it appears twice. So somewhere in this list here, we have v sub I equals v sub j, and where I is less than j, and they both equal U. So that would give you a segment like this here. Again, this would be U, this would be some vertices in between, then you would have U again. And this is a closed walk, right? You're starting at one vertex and returning to it. And that length would be j minus I, just subtracting the indices here. Then the remaining portion, Vj plus 1 up to v sub k, which is v0, and then kind of looping around and going to vi. So you're basically leaving this out. You're starting from here and going here, but in the opposite direction. So that's another closed walk of length k. That's the total length here, right? K minus the length of this closed walk. And then we have that K equals this plus this. And K is odd. So we're adding two integers together here. And when you add two even numbers, you get an even. And if you add two odd numbers, you get an even again. So that means one of these has to be odd. And so we choose that walk, and that would be a smaller closed walk of length, odd length. It could be a cycle, in which case we'd be back to this case. If it's not, we just repeat the process and keep selecting the smaller, the odd walk out of the two resulting closed walks, and eventually we're going to get a cycle. So that's the proof of the lemma. Okay, so two different ways of proving the initial theorem. One relied on this lemma here. So we have an example here of how to use our theorem 5. We have a graph, and we want to know whether or not it's bipartite, but our theorem says if we have an odd cycle, it's not bipartite, and we can see right away, I've highlighted in these dashed lines here that we do have an odd cycle, and so this graph is not bipartite. Bipartite graphs arise in matching problems. For example, consider a set of 5 people whose first initials are A, B, C, D, and E. So I have them here at the top of the graph. The 5 people are to select from among 7 prizes at a party. As you can imagine, I'm going to number the prizes 1 to 7. However, each person is only interested in some of the prizes. The prizes are numbered 1 to 7, as I just said. The preferences of the 5 partygoers are as follows. A prefers 1, 2, and 3. So you notice I've drawn an edge between A and 1, 2, and 3. B prefers 1, 3, and 4. 1, 3, and 4. And so on. C prefers 1, 4, 5. D, 1, 5, and 6. E, 1, 6, and 7. So we've represented the situation in terms of the partygoers and the gifts that they prefer using a bipartite graph. The problem is to assign, if possible, a prize to each person from that person's list of preferred prizes. In this case, the solution is fairly easy to visualize. A gets 1, so that 1 is now gone. B gets 4, so 4 is gone. C gets 5. D gets 6. E gets 7. And then we have everybody getting 1 gift. Okay, so that was more of a visual solution. It wasn't something that we computed using graph theory, but what helped us was being able to cast the problem in terms of a bipartite graph, so we can kind of go through visually and see how to do these assignments. So that was it for bipartite graphs in this lesson. A second type of graph I want to talk about in this lesson is the trees, and as well as forest, which we'll get to. So a tree is a connected graph that contains no cycles. So that's pretty easy. In the figure, these down here, T1 and T2 are examples of trees. You notice there's no cycle. A forest is a graph, all of whose connected components are trees. So graph F in the figure is a forest. So you see here we have a tree here and another tree here. So it has 2 components. By definition, a tree is a forest, but not the other way around. So a tree is a forest with just one tree in it, but A forest is not a tree, right? It's multiple trees. Then a leaf in a forest, or for that matter, a leaf in a tree, is a vertex of degree 1. So you notice most things here have degrees higher than 1, but this has degree 1, and then these things on the end also have degree 1. There's only one edge connected to them. So these are leaves here. This is a leaf, and this is a leaf. Then in our forest, these two are leaves. This is a leaf. This is a leaf. This is a leaf. And these three are leaves. In the previous lesson, the one on examples, we defined a tree as follows. A tree is an undirected graph in which every pair of distinct vertices is connected by exactly one path. So that's equivalent to what we just said on the previous slide. A tree is a connected acyclic undirected graph. Acyclic meaning no cycles. We then proved in this previous lesson a tree with n vertices has n minus 1 edges. So I just want to carry over this theorem in case we need to use it again. So point it out here a second time. If G is a graph where every vertex has a degree greater than or equal to 2, then G contains at least one cycle. Okay, so we proved these things earlier. A graph G is a tree if and only if every two vertices are connected by exactly one path. So effectively what we're going to show is the equivalence of two definitions for a tree. We'll show that a tree is a connected acyclic undirected graph if and only if every two vertices are connected by exactly one path. So the two definitions are the same, and we'll show that in this proof of this theorem. So going in one direction, if every pair of vertices in G are connected by a single path, then G is connected. So we have that part of the definition here. If G contained a cycle C, then any two vertices on C could be connected by two paths going in each direction, which contradicts the initial assumption. So G must have no cycles, and by definition G is a tree. So we've shown it in the theorem in this reverse direction. So going in the other direction, assume G is a tree. By definition, we know that G is connected, and thus every two vertices have at least one path between them. Assume two vertices U and V are connected by two different paths, P and Q, and I drew it down here. So you have U and V, and then there's two paths that connect them. P is the one on top, Q is the one on the bottom, and the complication is that P and Q may overlap. So, however, starting from U, there must be a first vertex X on P and Q such that the next vertex on P and Q leading to V is different. So in other words, you have overlapping up to some initial point X, and then you go from there, P and Q separate. Further, P and Q both terminate on V, therefore there must be a first vertex Y after X leading to V that is on both P and Q. So that's this here. So this is the first time they meet. Now it's possible they separate again and come back together again, but we're just interested in the first time the two paths meet again after this point X here, this vertex X here. And just note here, X and Y cannot be the same vertex, since P and Q would be the same path in that case. The path from X to Y on P and Q have no vertices in common and have the same starting and end vertex. So we're just talking about this path and this path here. And thus, they form a cycle that contradicts the initial assumption that G is a tree. So U and V, which we selected arbitrarily, are only connected by a single path, exactly one path. Okay, so that just shows that you can use either definition for a tree, they're equivalent. You can either assume the tree has no cycles in it, or you can assume there's for every two vertices they're connected by just a single path, exactly one path. If a tree has at least two vertices and it has at least two leaves, of course the tree with a single vertex has just that one vertex as a leaf, so we kind of leave that out of the theorem. But if you have a tree with two vertices and there's just the one edge between them and both of the vertices are leaves, so that's this first case here. The more interesting case is when you have three or more vertices. In that case, let P be a path of maximum length in our tree T. Represent P as the ordered list, V1, V2, V sub n. So these are vertices that are connected together. If V1 is adjacent to any other vertex in P, this would create a cycle, which is not possible since we're given the T as a tree, and we know trees don't have cycles. So V1 is not adjacent to any other vertex in P. If V1 were adjacent to a vertex V not in P, then we would have a longer path in P, V, V1, V sub 2, so forth, which contradicts our assumption about P having a maximum path, being the maximum path. So V sub 1 is only adjacent to V sub 2, and so V sub 1 is, by definition, a leaf. In a similar way, we can illustrate that V sub n is also a leaf, and that proves our theorem. I proved the following theorem in a previous lesson, the one on examples. I want to prove it again here. I'll make use of the theorem 7, the theorem we just proved on the previous slide. So here it is. If a tree T has n vertices, then it has n minus 1 edges. And we do proof by induction, as I did initially, but the first time I didn't have this theorem in hand. So for n equals 1, we have a tree consisting of a single vertex, and therefore the number of edges is n minus 1, which is 0. Right? There's no edges in that case. So the induction hypothesis is assume the theorem is true for n equals k, i.e. if a tree has k vertices, then it has k minus 1 edges. And then we want to prove that if we have a tree with k plus 1 vertices, that it has k edges. So by theorem 7, T has at least 2 leaves. Remove one leaf and a single edge attached to the leaf. This leaves us with a tree T prime, a tree with k vertices. By the induction hypothesis, T prime has k minus 1 edges, thus T has k edges, since we just removed the single edge to go from T to T prime. Okay, so that proves this theorem in a slightly different way from what I had done before. This slide and the next are about subgraphs. As you might suspect, the subgraph of a graph is sort of a subset of your graph. So I have a formal definition here. A graph H is called a subgraph of graph G if every vertex of H is a vertex of G and every edge of H is an edge of G. Okay, so that's pretty straightforward. If H is a subgraph of G having the same vertices of G, but not necessarily the same edges, then H is a spanning subgraph of G. So we have a couple of examples here. In the figure, H and K, so these two here are subgraphs of G. You can see H here is just this little bit in here of G, and K is sort of the scaffolding for G. It's here, here, and here, but we eliminate some of these edges when we construct K. Further, K is a spanning subgraph of G. So you can see here spanning means same vertices, but not necessarily the same edges. So you can see here we have every vertex in G is also a vertex in K. It's just that we have fewer edges, and you can get the sense of the term spanning. You can still get between all the different vertices here with fewer edges than you have in G. And then clearly H is not a spanning subgraph. It doesn't have the same vertices. We don't have these two here in H. The same graph can be drawn in multiple ways, and in many cases it is far from obvious that the graphs are the same structurally. For example, the figure below here depicts three different renderings of the same graph. This is known as the Peterson graph. It's used in a lot of different examples and counterexamples. So these three are the same, and of course they don't look at all similar. It would take some effort to kind of sort out and convince yourself that they are. One way to do it would be to, for example, take this one in the middle and give labels to every vertex and labels to every edge, and then map that to the edges and vertices in either one of these two here. So it's a bit of a complex process. So just one cautionary note. I mentioned this earlier, but in another lesson, but I'll mention it again here. Where the edges crisscross here and I don't have a vertex, there is no vertex here. That's just an issue of trying to draw this in the plane. Same thing here. This is not a vertex, this point. That's just where they're crisscrossing, and you have the issue here and here. So the only place you have a vertex is where I actually have this dark black dot. Two graphs are said to be isomorphic if they have the same structure. In other words, graphs G and H are isomorphic if the vertices and edges of G can be relabeled to produce H, or vice versa. More formally, graphs G and H are isomorphic if one can define a bijection between the vertex sets of G and H, i.e. some function f between the vertices of G and the vertices of H, and the function is a bijection, such that any two vertices U and V of G are adjacent in G if and only if the mapping of FU and VFV are adjacent in H. So I have an example to maybe clarify that a little bit. So here's our G and here's our H, and we want to do this bijection. So you see here I have the vertex by vertex mapping. So we map A to 1, and you can see what I've done here. I've just flipped this to the other side of the line, and everything else is pretty similar. B gets mapped to 2, C to 3, D to 4, E to 5, F to 6, and G to 7. So wherever you have a adjacent pair here, you would have an adjacent pair here. So for example, between G and A, you have an edge. And then if you look at what G and A are mapped to here, it's 1 and 7. And so you have an edge between 1 and 7, just as an example. Okay, so that was it for this lesson. I have a couple more lessons in this series on graphs. I have one on connectivity, and then I have a final lesson on some exercises based on the material from the previous lessons.